Moving on to our third gas law, this is called Gay-Lussac's law. It's the last gas law that will be similar to the two you've already done. The next gas law is a little bit simpler. So Gay-Lussac's law says a pressure of gas varies directly with its Kelvin temperature if volume is held constant. So now volume is held constant. We won't be dealing with that. Pressures in atmospheres, Kelvin temperature and Kelvin scale, and a direct relationship. So if one goes up, the other goes up. If one goes down, the other goes down. So the equation for this is P1 over T1 equals P2 over T2. Once again, ones stand for original or initial pressure and temperature. Twos stand for final or new pressure and temperature. And like I said before, if you want to just memorize the cross-multiplied version, it would be P1 T2 equals P2 T1. I like that version, but that's just me. So, first example, I didn't have a good visual for this one, I apologize. Gas in an aerosol can is at a pressure of 3 atm and a temperature of 25 degrees Celsius. So P1, 3 atm, T1, 25 degrees Celsius, add 273 to get to Kelvin, and we get 293 Kelvin. Have to be in Kelvin, have to be in ATM. The label on the can states that the can should not be in an area that exceeds 52 degrees Celsius. Change that to Kelvin. .325 Kelvin. What will the pressure be at this maximum temperature? So we're asking, what will the pressure be if the can is at its maximum unsafe temperature? So P1 over T1 equals P2 over T2. I like to cross multiply them, so I get P1 T2 equals P2 T1. And I'm solving for T2. Divide both sides by P1. So T2 equals P2 T1 all divided by P1. Plug in my numbers. P2, whoops, I lied. Let me go back, guys. Sorry about that. Were you thinking, what is she doing? I'm not solving for T2. I'm solving for P2. All right, dragon. Hopefully you are on the right track. Okay, solving for P2. I'm going to divide both sides by T1. There we go. Those cross out. So P2 equals P1 T2 over T1. Now I can plug them in. P1, 3 atm, times T2, 325 Kelvin, all divided by T1, 298 Kelvin. And I get 3 times 325 divided by 298. I get 3.27 atm. So Gay-Lussac says if pressure goes up, temperature goes up, or temperature goes up, pressure goes up, then if pressure or temperature goes down, the other one goes down. So what happened here? Temperature went up, pressure should go up, 3, and then it was 3.27, so yes, it did go up. Check yourself. You could also just plug it into this equation. You can know if you have the right answer without me even looking at it. All right, let's try another one. At 120 degrees Celsius, the pressure of nitrogen gas is 1.07 atm. What will the pressure be at 205 degrees Celsius if volume is held constant? Remember, we don't care about volume. So this is T1, P1, T2, and I'm finding P2 again. Remember, I have to change my numbers to Kelvin. So add 273, and I get T1 is 393 Kelvin. And then once again, for P2, add 205 plus 273. 478 Kelvin. All right, P0 is on top, T0 on the bottom. Cross multiply if you want. You don't have to write both methods, whatever you're going to use. And once again, solving for P2, divide both sides by T1. So P2 equals P1, T2, T1. Plug it in. P1, 1.07 ATM, times T2 in Kelvin, divided by T1 in Kelvin. And I get the new pressure is 1.07 times 478 divided by 393. I get 1.3 atmospheric pressure. Check it out. Pressure went up, it increased, and temperature went up. So we're good. That is Gay-Lussac's law.